Well, the purpose of this video is to take another look at the historical tangent line problem with a little variation just for the fun of it, you might say. The tangent line I'm going to look for is going to be the line tangent to the graph of this function here, stated in blue. It can be a parabola. A point on that parabola, one of the points would be negative 1, 3. I want to take a look at the tangent line, tangent to the graph of that parabola at that point. And playing around with it, I'm drawing the tangent line partly in red and partly in green. And you're also going to see two triangles drawn, one of them red and one of them green. The red one is going to relate to the red part of the tangent line and the green one to the green part of the tangent line. The triangles are going to be animated and keep getting smaller in each iteration of the animation. And the animation is going to actually keep repeating itself as long as I let it. And I've created a connection between the red and green portions of the tangent line and the red and green triangles. And this connection we'll look at in a moment. The red tangent line portion of the tangent line, its length is going to equal the ratio of opposite to adjacent lengths relative to a particular angle in this triangle that I mentioned. And the green tangent length, the length of the green portion of the tangent line, is going to be this opposite over adjacent, again relating to the green triangles. Now, what is it going to look like here? Here's your tangent line to the graph of the parabola. Parabola's in blue. Tangent lines drawn in partly in red, partly in green. And we got these two triangles being drawn here. Didn't animate the opposite and adjacent, but what you're going to have going on here is that the triangle, the green one, is determined by the point of tangency and another point on the parabola, and then going straight down, straight over, form a right triangle. Same thing with the red one. And the length of the green portion of the tangent line is equal to the ratio of the opposite to adjacent sides of the green triangle relative to this angle in here. The same thing with the red triangle. The ratio of opposite to adjacent side lengths relative to this angle in here is going to give you the length of that portion of the tangent line. Now, these opposite divided by adjacent ratios are actually giving you the slope of the hypotenuse of the green triangle in the green case and the red triangle in the red case. And what happens, it turns out, is that the triangles get smaller and smaller as one of this point up here gets closer and closer to the point of tangency, and the point down here closer and closer to the point of tangency. This opposite divided by adjacent, giving you the slopes of the hypotenuse of the green and slope of the hypotenuse of the red triangle. They're each approaching the same number, and that number is going to be the slope of the tangent line at this point right here, negative 1, 3. Now let's stop the animation and look at it in a still. So here's opposite, here's adjacent relative to this angle down here. Here's opposite, here's adjacent relative to this angle up here. What's happening at this point is moving closer and closer to that point of tangency. And as it does, the triangle is smaller and smaller. And you'll notice the hypotenuse of the right triangle starting to move over in this direction, getting closer and closer in direction, in slope, to the slope of the tangent line. And the same thing with the red one. As this point keeps moving up here, the hypotenuse of the right triangle formed will start moving over again towards the tangent line. Its direction would be approaching the direction of the tangent line, approaching the slope of the tangent line. So the slope of each hypotenuse is going to be approaching the slope of the tangent line. That's my claim here in this pictures. These pictures. And I've also drawn this so that the actual value of the slope of the hypotenuse of the right triangle is reflected in the length of the green portion of the tangent line. And the slope of the hypotenuse of the green triangle is going to be reflected in the length, represented by the length of the green portion of the tangent line. If we play the animation again, what you'll observe happening is the actual red portion of the tangent line getting smaller, the green portion getting larger. Both of them are approaching the same length. If the triangles get this small here, the actual hypotenuse of each right triangle is pretty much indistinguishable in direction, in slope, that of the tangent line. If I told you that the slope of the tangent line was either 1, 2, 3, or 4, could your understanding of slope actually cause you to figure out what, looking at this picture here, what must be the length of the green portion of the tangent line, or approximately what number it's approaching? If it's 1, 2, 3, or 4, because it actually is 1, 2, 3, or 4. In this little MP4 player here, we can actually come down here and sort of stop a few of these steps in the animation, and you can see the triangle is getting smaller and the hypotenuse of each triangle starting to be almost indistinguishable in direction, in slope, from that of the tangent line, leading us to the notion of something called a limit that's coming in your calculus course. If you're looking at this during my orientation video, if you're on YouTube, well, this is taken from one of my calculus classes. Now, what I'm going to do here is move on to the next slide in this PowerPoint. And it turns out this limiting length of the red and green line segment portions of the tangent line are actually approaching the slope of the tangent line at the point -1, 3. So looking at this blue parabola, point -1, 3, looking at the line tangent to the graph of the blue parabola at the point -1, 3. If you figured out what its slope was, could you find any equation of this tangent line? That's what I'm hoping everybody's going to be able to do. Let's actually show the taskbar here and pull up another picture. Some of you may like this one better. What I've got drawn here is my tangent line again drawing part of it in red, part of it in green, although the red and green portion are not going to change in this demonstration. Here's my blue parabola. Here's the point A, it's the actual point, -1, 3. And then what I've done is I've got a point B, I've called it, on the parabola that I'm going to activate here. What I'm going to do now is take this point B and move it, reactivate it, closer and closer along the graph of the parabola to point A. And points A and B are forming what's called a secant line, not the trig punching secant, but secant line, a line through 2 points on the graph of the parabola. And the slope of that secant line right now is 0.33. Nothing like the slope of these two tangents here, these two portions of the tangent line, which slope I'm now giving away is 2. But watch what happens. I take this point B and I move it, trying to grab it and move it. I got it now and I'm moving it. And notice now I got the whole secant line drawn, not just a little hypotenuse of a right triangle that keeps getting almost too small to see. You can see the slope of that line BA, that secant line, is changing as I move the point. And now it's up to 1.54. Here the point's coming down here closer to that point of tangency point. And what we can observe is that the slope of the secant line is now about 1.8. Can hardly tell it from the tangent line. If we move point B a little closer to point A, up to 1.96, getting very close to the slope of the tangent line. In fact, if I move it literally on top, A and B on top of each other, now they're not exactly on top of each other. You try to compute the slope of the secant line, you couldn't do it because you just have 1 point. But they are so close together, almost infinitesimally close together, you can't really tell them apart. And notice the secant line now is being displayed with a slope of 2.00. To at least as many significant digits as I'm displaying, we've got that secant line having the same slope as the tangent line. If I actually take the point and move it on down below, notice my right triangle being drawn on the other side from the previous animation, but the same basic idea going on. And now the secant line is actually steeper than the tangent line. It does have slope equal to the slope of the hypotenuse of the right triangle being pictured here this time. Now if I move point B back up closer and closer to point A, watch that secant line slope going down to 2 now. And real close to 2, not quite 1.99. I'm back up above, come down below 2.02. Can't seem to get it quite on as accurate as I had it before. But the idea here is, whoops, let's see, we don't want that live. I just want this point alive. Is say this point moves point B closer and closer to point A. The slope of the secant line gets you approaching the slope of the tangent line. And limiting vein, here we've got it right at 2. It's the limiting value of that secant line as the second point gets closer and closer to the point of tangency that we're looking at. That is going to actually give you, and in calculus we define that to be the slope of that limit, to be the slope of the tangent line. In fact, if I go back to my my PowerPoint here, and we go on to our next slide, a reminder that a difference quotient for some y, a function of x, defined to be this right here, and notice that delta x in the denominator is just like x plus delta x minus x. Your difference quotient from algebra class is literally a representation of the slope of a line if you know 2 points on the line. If you've got a value for x and a value for delta x that's not 0, then this f of x plus delta x gives you a y value on your graph of your function corresponding to the x value of x plus delta x. And then f of x gives you another y value on the graph of your function corresponding to an x value of x. So you literally have like a y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1, the old definition of slope of a line. So your difference quotient is actually giving you the slope of a line through 2 points on the graph of your function, as long as your delta x is not 0. This point and that point, picking a value for x and a value for delta x, give you 2 points on the graph of your function. So in calculus, what we do here is we take this difference quotient and compute the limit as your delta x value gets closer and closer to 0, which is what was happening in the pictures I've been showing you. This, by the way, is the definition of something called a derivative in calculus. You also compute this limit by definition. It's going to give you the slope of the line tangent to the graph of a function at some point on the graph corresponding to whatever x value you're having here. But how can we compute this limit? Well, if our function was the parabola we just looked at, f of x equals 4 minus x squared, the derivative of that function right there being this limit. Literally, by definition, if you're limited to one word, a derivative is actually a limit. But it also can be used to find a slope of a tangent line. Now, this limit here is delta x approaches 0. This difference quotient, with that being the function, would look like this. You're replacing your x with x plus delta x, this thing here, and then minus your f of x, distributing or subtraction, we get this. If I square this thing here and do a little simplifying, 4 minus 4 is 0, and we're going to have a negative x squared plus x squared be 0. We're just going to be left with this, and you can actually factor a delta x out down here and get to this limit. And now we know that two limits are going to, this limit and that limit here, are going to be equal if the arguments for the limit differ by only, say, one possible value of delta x, which would be 0. If delta x was 0, this thing would be undefined, be 0 divided by 0. How would you compute the limit? Well, by direct substitution, you can compute it over here. If you divide out the delta x's, one of our calculus theorems tells us that this limit and that one will be the same if they exist, and they do, because this one right here you can compute by direct substitution. Put 0 in for delta x, you get negative 2x. So that limit that equals the derivative of this function here is negative 2x. Of course, we know if you're taking calculus that you got a differentiation formula that will actually produce that result immediately, but this does remind you of the limit processing where it came from. So at the point negative 1, 3 on the graph of our parabola, we can evaluate our derivative by replacing the x with negative 1. Our derivative at that point, negative 1, 3, would be negative 2 times negative 1, or 2. Well, that means that the slope of the tangent line at the point negative 1, 3 is going to be 2. And of course, negative 1, 3 is a point on the tangent line, so you can use the slope of 2 and the point negative 1, 3 to substitute into your point slope form for the equation of a line, which I've written down here. And so then putting in those values, replacing that x of 1 with negative 1, y of 1 with 3, we get this. And then we can clean that up a little bit, multiply that out, add 3 to each side of the equation. Nice little form for the equation of your tangent line. Y equals 2x plus 5. Equation of that tangent line we were looking at. I love this stuff in calculus. I gotta tell you, it's kind of cool that you can actually figure that out these days.